Hello, I'm Dr. George Bartuska with the Florida Aviation Network. Welcome to Sky Insights. Today we'll be talking about hurricanes, actually known as tropical cyclones in the meteorological world. I want to make just a quick statement. Because hurricanes are so large and infrequent, these storms are difficult to measure and model in computer software. Many aspects of the storm's dynamics and surface interactions with the oceans remain unresolved. Let's take a quick look at what we know so far. Now, tropical meteorology is a very complex subject. This is a one-semester class I'm going to do in less than 30 minutes, so let's see what we can get. Note, tropical cyclones, like I said, or hurricanes, are relatively rare. The required simultaneous preconditions are also relatively rare. However, the necessary conditions for formation are quite common in the tropics. Atmospheric conditions must be just right for hurricane formation. As we call it, the Goldilocks principle. It's got to be just right. Now, here's Hurricane Ian back in September of 2022. We can see we've got radar imagery on the left, we've got satellite imagery on the lower right, and we have a historical track in the upper right. What I always tell my students to do, and we do in class, is we learn to plot the hurricane on a hurricane tracking chart. You can download these off the internet. Make sure you get one that's got the longitude and latitude lines marked well enough that you can pick them up with a ruler. And if you take the time to model that storm, you will know where it is. But remember, a hurricane is not a track. It's not a line like a tornado. It's a storm that's usually average 300 miles in diameter, which is the length of the Florida Peninsula. Here I have about a 50-mile diameter circle just for this tracking. Now, this is a video of storm surge that was taken by a storm chaser. He mounted a camera up on a utility pole. He doesn't allow his video to be played online in a session like we're doing, but you can go onto his website. It's called Max Olson Chasing, and you can watch this live video. But I want to set the scene. You see the red structure, the red building with two garages. To the left is a hotel, and to the left of that, about 100 feet, is the Gulf Coast, and this is in Fort Myers, and the storm surge is starting to come ashore. Now the storm surge has come ashore and the water is up to the top of those garages, which is about 10 feet. Here the building's starting to come off the foundation. Here it's come off the foundation. Here it's starting to go down the street. Now it's gone down the street and it's gone, and this is about 3 hours later. So storm surge for people that live near the coast is one of the biggest problems. What is a hurricane? A hurricane, or a tropical cyclone, is a rotating vortex with deep organized convection and a closed wind circulation around a well-defined center, with maximum sustained winds of at least 74 miles an hour or 64 knots, and they originate over the tropical oceans and driven principally by the heat transfer from the ocean. Both the sensible heat that we can feel and the heat from latent heat from condensation, which I'll talk about in a minute. Now, there's 80 to 90 tropical cyclones, and let me go over to that again. All of these rotating storms are tropical cyclones in the meteorological world. But in the Florida, in the North Atlantic, we call them hurricanes. The size averages 300 miles in diameter, which is the length of the Florida Peninsula, but they can be as small as 100 miles an hour, 100 miles in diameter. They can be as large as 1,000 miles in diameter. They all vary, they're all different. Storm forward speed, if any, averages 10 to 15 knots. The expected path and intensity is very difficult to predict. Now, here's back at the 2004 hurricane season, where we had 4 hurricanes cross Florida, but 3 of those hurricanes crossed central Florida. Notice they're drawn as lines, but like I said, you need to think of that storm as having a swath. Instead of thinking of a edger, think of a lawnmower, think of a rotating something to give it some size. Here's the swath from data after the storm. This is a typical long landfalling hurricane, where you can see the red is the most intensive winds at 110 to 120 miles an hour. And as it comes across the land, it loses some of its intensity. But once it exits the land, it'll intensify again if there's warm water. Here is an unusual but much different hurricane, Hurricane Charlie. Hurricane Charlie was almost like an intensive tornado. It was moving quick, intense winds. And here was Hurricane Jeannie. This one, again, was kind of a typical hurricane where it made landfall and started to slow down. Now, hurricanes are dangerous. They cause major damage from storm surge, wind damage, rip currents, very underestimated problem with rip currents, flooding, and tornadoes. We're here to talk about aviation. Who's at risk? Now, remember what I said? They're all tropical cyclones, but in the Pacific, we call them typhoons. In the Atlantic, we call them hurricanes. In the Indian Ocean, we call them tropical cyclones. Around Australia, they have a bunch of different names, but the meteorological name is a cyclone. But in the maritime industries, in the navies, in the super tankers, and in the container ships, that industry refers to them as tropical revolving storms. Now, who's at risk? This is a very common image that's in most publications, but all it shows you is where the hurricanes make landfall. This is the important diagram that shows you really who's at risk, because that hurricane is carrying billions of gallons of water with it, and it's going to give it up somewhere. If the hurricane recurves and goes out in the Pacific, in the Atlantic, it'll eventually dump that water in the ocean. But if it doesn't, it's going to dump that water somewhere in that image. Now, we're going to talk a little quickly about tracks in just a minute. September 10th is statistically the most likely day to have a hurricane based on data from 1944 to 2020. That does not mean there'll necessarily be a hurricane on the 10th. It just means that's the peak of the hurricane season. Now, hurricane formation. Anytime there's warm tropical ocean water of at least 80 degrees Fahrenheit or 27 degrees centigrade down approximately 300 feet. You've got to have a mass of hot energy for that hurricane to suck up. Official hurricane season is June 1 through November 30th, but most tropical storms form in late summer, early autumn, August, September, October. Hurricane lifespan. The average lifespan is 10 days to 2 weeks, although we've had some last a month. On the average, there are 6 hurricanes that impact the United States every year, but it only takes one. Now, we generally talk about the climatology. How do we come up with this hurricane season? Notice June and July, there's not much activity. Starting in August, things crank up. September is usually the maximum year. October can have some severe storms also. I said the water's got to be at least 80 degrees. This is August of 2023. Look at the water. We have 87, 90 degrees, 85. There's no problem with energy in the water. What are the deaths from in a hurricane? Originally, it was the storm surge was the biggest problem, but the National Weather Service released a new image last week that I don't happen to have a copy of. Rip currents have overtaken storm surge because people now understand what storm surge is and need to get away from it. But too many people want to hang out on the beach and see the effects of the hurricane, and they're drowning in storm surge. Now, what's that hurricane do? Let's take a look at storm surge. This is Hurricane Katrina back in 2005. This is on the coast of Mississippi. You can see the house on the left before the hurricane. Nothing on the right but the tree after the hurricane. Inland flooding. Remember I said a typical hurricane has 60 billion gallons of water. It's going to give it up somewhere, and it's going to cause severe inland flooding. High winds. We can have winds up to 150 to 200 miles an hour, and they're going to do damage. Some hurricanes spawn a lot of tornadoes. And now let's take a look at the actual hurricane if you're not familiar with one. Let's look at that cross section in the lower right. The hurricane in the middle has an eye, and around the outside of the eye is an eye wall. Think of it kind of like a funnel. It turns out the eye wall is the most intense, dangerous part of that hurricane. Going up to the upper right picture, you can see there are all kinds of bands around the hurricane at the low level. We call those rain bands, and we'll look at those now. Here you can see those rain bands. There can be one eye wall, there can be two eye walls. Generally, the outer eye wall is in the process of taking over the inner eye wall in what we call an eye wall replacement cycle. But you can see those rain bands, we call them inner and outer, or primary and secondary. That's the first thing that's going to impact you if a hurricane's coming towards you. And they can have intense thunderstorms, rain, lightning, etc. This is a computer simulation of one. And once again, you can see we have a couple eye walls and we have lots of rain bands. Now, I'm going to use an example. This is a cross-section of a radar output from Hurricane Andrew in 1992. Hurricane Andrew is still the worst hurricane to ever hit the state of Florida. Let's look at the spiral rain bands. They extend out 100 to 500 miles. They're intense, organized thunderstorms with shower cells. Last time I talked about thunderstorms, so basically a hurricane is just a group of intense thunderstorms. Between the rain bands, we have stratiform precipitation, and we can have primary and secondary or inner and outer rain bands, thunderstorms with heavy rain, strong winds, tornadoes, also convective bands and straight hurricane squall lines. So when you think of a squall line out Midwest, you think of a line of thunderstorms. Here, that line of thunderstorms is what the rain bands are. Now, the eye wall in the middle of I said the middle of the hurricane has an eye, but that reddish part around the eye that looks like a big donut, that's the eye wall. That's the heart of the hurricane, made up of short segments of monstrous thunderstorms, similar to a mature mesoscale convective system that we talked about last time. Inward and outward spiraling winds, I'm going to show you in a minute. Vertical or slanted outward wall, I'm going to show you that in a minute. This is where the fiercest winds and heaviest rainfall at 1,500 to 3,000 feet above sea level are. Typical winds are 115 to 150 miles an hour. In excess of 200 mile an hour winds have been recorded. Ocean waves below the eye wall are 15 to 40 feet. Strong hurricanes exhibit double eye walls with a moat in between, and like I said, that's usually during the eye wall replacement cycle. Here we have a image on the left from Hurricane Hunter aircraft. Hurricane eye wall can be vertical, but typically slopes up and out, referred to as the stadium effect or cereal bowl shape. On the right, we have a cross-section of radar imagery going up 1,500, 8,000, 15,000. And by looking at this diagram, you can see why the hurricane hunters generally fly in between 8,000 and 10,000 feet where there's much less wind so they don't endanger the aircraft. Now the eye, the actual center of the hurricane, that's the most recognizable feature of the storm. It's the storm's axis of rotation, typically nearly circular or elliptical. There's sinking and warming airflow going down into the eye. Usually it's calm, free of high clouds, can be clear to scattered low clouds. Typical eye is 20 to 40 miles in diameter, exceptionally low air pressure. Smaller eye generally means a more intense hurricane. And this is one of the oldest phenomena known in the science of meteorology. Now here's a good picture of that picture from the Hurricane Hunter. In the foreground is actually a cloud base that's in the eye, but above that you see the slanting out eye wall. And here's another picture of a hurricane from space. Now today we look at hurricanes using satellites, ground and airborne radar, aircraft weather balloons, GPS radio zones, GPS drop wind zones. However, before the 1960s, before satellites and sophisticated radar, this is what we had to tell how bad a hurricane was. This is a plot from a barograph. Where that line dips down the lowest was the lowest barometric pressure, but you would only get this if the hurricane went right over your station and the hurricane didn't destroy the station and the barometer. Here's what that microbarometer looked like. Here on the inside it has a set of bellows. I'm going to hold this up real quick. These are the bellows, and this is there we go. This is exactly what's inside your aircraft's barometer. Here's the barometer. Whoop, there's the barometer. These are the bellows that are inside the barometer, and this is what's inside the microbarograph. Okay. Okay, so that's all we had before. We still use these, but they're all electronic now. Now, the sun is the energy for all of Earth's weather, and it's definitely the energy that heats up the water that's going to feed the hurricane. However, there's got to be water vapor in the atmosphere. Without water, we don't get thunderstorms, we don't get tornadoes, we don't get hurricanes. Now, last time when I did thunderstorms, I went into the partial lifting of air and in the instability. I don't have time for that today, but I want you to know that everything that drives a thunderstorm, rising air to the lifted condensation level where the dew point is, the creation of positive buoyancy, and then the updrafts up to where the water gets used up during condensation, that's exactly what's happening in the eye wall of the hurricane. This is a picture from a weather book on gliding, which has an excellent diagram. That initial rise is known as the dry adiabatic lapse rate. Through the cloud, it's the saturated or moist adiabatic lapse rate, and once it leaves the cloud, it's back. This is called the lapse rate. It's back to the dry adiabatic lapse rate. Now, anywhere there's water and land on planet Earth, there's the potential for a sea breeze. The solar radiation is at the wrong wavelength to heat the air, barely heats the air. So it'll heat the ground, and the ground will re-radiate and heat at the right wavelength to heat the air. So the air on planet Earth is heated from the bottom up. If it gets heated near the water, as the air starts to rise and create an updraft, it'll pull in air over the water, and that'll create the sea breeze. The unique thing that happens in Florida, in the Florida Peninsula, is we have the Gulf on one side of the state and the Atlantic Ocean on the other side, and thus we get a dual sea breeze. You can see in this animation the air is coming in from both coasts. And if there were no other weather systems in the rainy season in the summer in Florida, we'd have thunderstorms right up and down the middle of the state. But there usually is something else going on, so it tends to move around a little bit. Now, this is one of the most standard historical plots we have of a cross-section of the eye wall of a hurricane. And what I've done is taken that and flipped it over and put another image right next to it to give you an idea of what a cross-section through a whole hurricane would look like. It's probably a little too close together, but I want to call your attention to those arrows on the bottom of the picture. I'm going to back up to the other one. You can see those arrows coming in. They come in and they go up through the eye wall, just like the updrafts in a hurricane, in a thunderstorm. And that intense flow is what drives the hurricane. So the hurricane starts out as a group of thunderstorms, and we'll go into that in the middle. But now I want you to look carefully at this picture. Notice in the middle of this image, there's nothing. That's the equator of planet Earth. Storms can't form at the equator because we don't have any Coriolis effect or the effect of the rotation of planet Earth. So we've got to be 5 degrees, approximately 5 degrees north or south of the equator to be able to form a hurricane or a tropical cyclone. What happens then? This Coriolis effect in the northern hemisphere causes things to go to the right. So in the image in the very middle, this is Hurricane Daniel in 2006 in the northern hemisphere. As these winds get sucked in, they're turning to the right, and the global effect is to turn the storm to the left. So hurricanes rotate counterclockwise in the northern hemisphere. In the southern hemisphere, it's just the opposite. Here's a visualization. The image on the left says vertical cross-section of the hurricane, a schematic. Basically, that's the eye wall. The air is coming in and it's spinning and it's going up through the eye wall and it's being exhausted. On the right is another image of that. It's very hard to see in this picture, but we have air coming in through the bottom and going up through the eye wall. Once it goes up through the eye wall, it's exhausted at 50 to 60,000 feet, but some of it comes back down into the eye to cause the eye. And as we know, in the case of a figure skater, when the figure skater pulls their arms in, they can rotate faster. It's what we call the conservation of angular momentum. And thus, the tighter the eye wall is, the more intense the wind can be. Now, what's the formation of a tropical cyclone or hurricane? You can see that's the African continent on the right. Most of the storms that eventually affect the United States form over Africa or over Ethiopia, where there are knife-edge mountains sticking up. As it comes across the African continent, usually in what we call the intertropical conversion zone. If there's enough moisture available, we're going to get a tropical wave or an easterly wave. As it continues to move, it can turn into a tropical depression if the conditions are favorable. And eventually we get rotation from the Coriolis effect and we'll have a tropical storm if the winds are 34 knots to 39 miles an hour. Once it reaches hurricane winds of 64 knots or 74, we call it a hurricane. Right now, we have a couple storms in the Caribbean, and they're not doing anything because there's so much upper aloft wind to tear them up, and we have all kinds of dust still coming off the African coast. How fast can all this happen? This is Hurricane Irma in 2017. In 3 days, it went from a depression to a hurricane. So it all depends on the condition. What's the most dangerous area of the hurricane? It's what we call the right front quadrant. The hurricane is turning counterclockwise, and yet this one is moving to the northwest. You add the wind speed in the hurricane to the forward motion, it's going to be highest wind speed in the right front quadrant, lowest wind speed in the left rear quadrant. Now let's take a look at these tracks. This is the part you got to pay attention to if you're anywhere near the coast. Hurricane motion. Tropical storms go where the planetary winds they are embedded in takes them. So do clouds, so do thunderstorms, but it's a real big deal with tropical cyclones or hurricanes. And the comparison we give is a cork in a stream of water. That cork is going to go wherever that water takes it. Hurricane tracks. Storm tracks can wobble, turn, make loops, wiggle, curve back on its track, meander back and forth, slow down, and stop. And we've had hurricanes stop in Florida. Here's some examples of tropical cyclones in the Pacific. They do all kinds of things. Now, one thing I want to point out, in the Atlantic Ocean, the distance between Africa and the United States is about 5,000 miles. In the Pacific Ocean, which is almost half of the globe, the distance from North American continent to, say, Japan is about 8,000 miles. So there's a lot more area for the storm to grow in the Pacific than there is in the Atlantic. And in the Atlantic, we call them hurricanes. In the Pacific, we call them typhoons. Right now, there is a system hitting Hawaii, the big island of Hawaii as we speak. It's Tropical Storm Lala, and this morning it went from being a tropical storm to a hurricane, but they only expect it to be a Category 1. Hopefully everybody there is ready for it. Oh, there it is. Good. There's Lala right over the top of the big island of Hawaii right now. So they're going to have winds of probably 70 to 90 miles an hour, and it's expected to dump 10 to 20 inches of rain. I've been there before. It's going to be an incredible thing. Now, let's talk about that storm surge again. This is a very famous situation that's in all the books on hurricanes. This is Hurricane Camille in 1969. This is the coast of Mississippi. That's the Rickaloo Apartments on the top view. That's a 3-story apartment building. 15 people approximately decided to stay behind and have a hurricane party. Below is what was left after the storm surge. Basically just the foundation and the swimming pool. Of those 15 people, one lady survived. She was found hanging on to a telephone pole about 5 miles away from the location. Now let's talk about aviation. Recommendations from the Aircraft Owner and Pilots Association. First off, if you're anywhere near the coast, consider buying a space in a hangar built since 1992, because since Hurricane Andrew, all the building codes went up. Securing your aircraft outdoor. Look for an open space clear without blowable objects. Try to find somewhere where something isn't going to blow into your plane. But remember, the wind direction is going to change as the storm goes by. If you're in the area during the tie it down upwind, secure latch doors and windows, and cover engine inlets, pitot tubes, and static ports. Wheels, chalk the wheels and set the parking brake. Secure to anchored cables and or dig a hole to put each wheel in, and deflate the tires to keep your aircraft in place. Note, check your pilot operating handbook for system for heat expansion on the brake. It may tell you not to set the brake. If somebody's going to move your aircraft to deal with the changing wind speed, don't set the aircraft brake. It all depends. Control locks. Make sure your control surfaces can't move or flap around in high winds. Install internal and external gust locks. Avoid looping a seatbelt around the controls, because this could set the controls in a climbing turn, which is exactly what the aircraft will attempt to do in severe winds. Tie downs. Always use tie down rings, not any other part of the aircraft. Use nylon or and I'll show you a picture of that in a minute. Use nylon or Dacron rope or chains. Don't use old manila rope. Try to position the tie downs at a 45-degree angle. In the left picture, you see a tie down ring or eye, and in the right-hand side, you see that plane being tied down at a 45-degree angle. Now, let's do a review. The meteorological term for a hurricane is a tropical cyclone. There are 80 to 90 tropical cyclones worldwide per year. Size averages 300 miles in diameter, but they can be as small as 100 miles. They can be as large as 1,000 miles. All tropical cyclones are unique. They're all different. Storm's forward speed, if any, averages 10 to 15 knots. Although hurricane season is officially June 1 through November 30th, most hurricanes occur in the autumn during August, September, and October, with September being the most active. The most dangerous area of the hurricane is the right front quadrant. The most intense and violent weather in a hurricane takes place in the eye wall. Storm wind speed must reach 64 knots or 74 miles an hour to be labeled as a hurricane. The eye of the hurricane is usually calm and possesses exceptionally low pressure. For a hurricane to form, conditions must be just right. The movement of a hurricane depends on the prevailing winds. Remember the cork in a stream analogy. Most fatalities, deaths during landfall hurricanes take place due to coastal flooding during a storm surge, and now we know during rip current, sorry, thank you. Hurricanes do not form close to the equator due to the lack of rotational energy from the lack of Coriolis effect. The thermal energy that powers a hurricane is primarily from latent heat during condensation. There's sensible heat just from the evaporation of the water, and then as the water is picked up in the updrafts and water condensation takes place, it gives up the heat. We call it latent heat. Primary physical processes fueling a hurricane are evaporation and condensation. September 10th is statistically the most likely day for a hurricane. Prior to radar and weather satellites, we used recording barometers. The sun is the primary source of energy for all weather on Earth. Now, in just the 2 minutes I have left, we all know about the hurricane hunters. Colonel Joseph Duckworth and his navigator, Lieutenant Ralph O'Hare, back in July of 1943 near Galveston, Texas, made the first penetration with an aircraft into a hurricane in an AT-6 trainer. Then we would use B-29s after World War II, then DC-6s, along with Lockheed Super Constellations. Today, for the research part, NOAA uses 2 Lockheed Electras. There's one taken off from Lakeland. It's going to swing around. One of them's called Kermit, one of them's called Miss Piggy. This is obviously Kermit. Okay. And here's the normal hurricane hunters that are always going out to get data for the National Hurricane Center. These are the 53rd Weather Reconnaissance Squadron, known as the Hurricane Hunters. They fly out of Keesler Air Force Base in Biloxi, Mississippi. They have 10 WC-130J Hercules aircraft. They describe their mission as a roller coaster inside of a car wash when they're flying through the eye wall. All those pilots are volunteers. Most of them are airline pilots. There's another good look at that eye wall, and that concludes what I have. Thank you for joining us. This is Dr. George Bartuska with the Florida Aviation Network. I'll see you next time for another weather topic. Now stand by for the number for your wings credit.